very important theorem, that is the Gauss's Divergence Theorem, that states if f vector is continuously differentiable vector point function. Continuously differentiable means the function itself is continuous and also its derivative exists. So if f vector is continuously differentiable vector point function in a region V and S is a closed surface enclosing V, then the surface integral of f vector dot product with n vector ds is equal to the volume integral of divergence of f vector dv, where n vector is a unit outward drawn normal vector to the surface S. So before starting with the proof, let's recall few points. So the remarks are written over here. If the outward normal to the surface S at point P makes angle alpha, beta, gamma. Suppose this is your surface S and this is your point P. So if the outward normal makes angle alpha, beta, gamma with the positive directions of x, y, z axis respectively, then the direction cosines of the normal are, yes, L is equal to cos of alpha, M is equal to cos of beta, and N is equal to cos of gamma, right? Now as n vector, that is the outward normal drawn to the surface S, is equal to cos alpha I vector plus cos beta j vector plus cos gamma k vector. And because of the direction cosines, I am writing L I vector plus cos beta is M. So this is mj vector plus nk vector. And if I take the dot product of n vector with I, so what I am getting? I get n vector dot product with I vector equal to, yes, L, only L, right? So in particular, that is, it is also equal to cos of alpha. So in particular, the dot product of n vector with I vector is cos alpha. Dot product of n vector with j vector is cos beta. And dot product of n vector with k vector is cos gamma. Please remember these. We are going to use this result in the proof of the theorem. Now let f vector is equal to f1 I vector plus f2 j vector plus f3 k vector. Where f1, f2, f3, these are the components of f, right? Then the dot product of f vector with n vector. It is writing the f vector first and taking its dot product with n vector. What should I write in place of n vector? Yes, it is Li vector plus mj vector plus nk vector. So that is equal to f1l plus f2m plus f3n. That is further equal to f1, what is L? It is cos of alpha, plus f2, it is cos of beta, plus f3, it is cos of gamma, where L and N are the direction cosines of the normal. Thus, the surface integral of dot product of f vector with n vector ds, that is equal to the surface integral of, yes, writing in place of this as f1 cos of alpha plus f2 cos of beta plus f3 cos of gamma ds. That is equal to integral over s, that is f1 cos alpha ds plus integral over s f2 cos of beta ds plus integral over s f3 cos of gamma ds. Now what is cos alpha ds? It is the orthogonal projection of area ds on yz plane. That is equal to, because the plane is yz, so writing this equal to dy dz. Similarly, ds cos beta, this is the orthogonal projection of area ds on zx plane. So that is equal to dz dx. And then ds cos of gamma is orthogonal projection of area ds on xy plane, right? So this is equal to dx dy. Fine. Please remember this. We are going to use this result also in the proof of the theorem. Now, if ds is the elementary area of the surface S at a point P, so therefore ds is equal to dx dy divided by cos of gamma. That is, ds cos of gamma is equal to dx dy, as the projection is on the plane xy, right? So writing ds cos gamma as dx dy. So taking ds cos gamma equal to dx dy. So from here, what is ds? It is dx dy divided by cos of gamma, right? And further, this is equal to dx dy divided by, what is cos of gamma? It is dot product of n vector with k vector. It is better to take the mod, where k vector is the unit vector along z-axis. So this is your unit vector along z-axis. Right? So this is also a very important point that we are going to use in the proof of the theorem. So let's start with the proof. Let's choose the rectangular Cartesian coordinate system. This is your x-axis, this is your y-axis, this is your x-axis, this is your y-axis, and this is your z-axis. And this is your z-axis. Let S be the surface enclosing the region V, and let F vector is equal to F1i vector plus F2j vector plus F3k vector, right? Then, as we are going to prove that the surface integral of F vector with n vector ds is equal to the volume integral of divergence of F vector dv. So let's take the divergence of this F vector now. Divergence of F vector is equal to, that is, del dot F vector, that is equal to I vector curly by curly x plus j vector curly by curly y plus k vector curly by curly z, taking its dot product with F vector, that is f1i vector plus f2j vector plus f3k vector. So when you take the dot product, we get curly f1 over curly x plus curly f2 over curly y plus curly f3 over curly z. And now we need to take the volume integral of divergence of F vector. So therefore, the volume integral of divergence of F vector is equal to, yes, the volume integral of curly f1 over curly x plus curly f2 over curly y plus curly f3 over curly z into dx dy dz. Please mark this as 1. Let's consider the volume integral of this component. So consider the volume integral of curly f3 over curly z dx dy dz. Let R3 be the orthogonal projection of the region V in xy plane, right? If you consider any point in this R3, and that point be x, y, 0, because it is xy plane, so z is 0. So any line passing through this point meets the boundary of surface S at 2 points. That is the z coordinates of the points. Let me write this first. Let's write this first. Let R3 be the orthogonal projection of the region V on the xy plane and every line passes through the point xy0 in R3 meets the boundary of S in 2 points. So if we are going to draw the line through this point, it is meeting the boundary of S at 2 points. So writing these points as, let the Z coordinates of these points be Z is equal to phi xy and Z equal to xi xy, with the condition that, let's say, where xi xy is less than equal to phi xy. We denote the parts of the surface S corresponding to Z equal to phi xy as S1 and corresponding to Z equal to xi xy by S2, right? Respectively, right? Then this volume integral of curly F3 divided by curly Z dx dy dz. So that is equal to, taking this integral inside, curly F3 by curly Z with respect to Z, because we are getting the points in Z coordinates. And writing dx dy outside of this integral, taking the lower limit as xi and the upper limit as phi. So this is equal to double integral over R3. What is the integration for curly F3 over curly Z? With respect to Z, it is F3. So writing F3 xy, the upper limit is phi for Z. dx dy minus double integral over R3. So this is F3 xy and the lower limit is xi dx dy. Please note here, from the remarks we know that ds is equal to dx dy divided by cos of gamma, right? And we have written this further as dx dy divided by mod of dot product of n vector with k vector. Yes, from the remarks I am writing this note. So for dx dy, we are going to use n vector dot k vector into ds, right? Because we are changing dx dy to ds, so this double integral will be changed into now the single surface integral, right? And for phi, we have taken the part of the S to be S1. So this integral now becomes surface integral of F3 n vector dot k vector ds, right? Similarly, the other one, it is the surface integral over S2, because for xi we have considered the part of S to be as S2. So this is F3. So writing here dot product of n vector with k vector ds. Is it okay? Fine? Alright. Now when we sum up these two integral, we are going back to our integral over S, because the S surface is divided into two parts, S1 and S2, right? The integral over S2 will change the sign, but the magnitude remains the same. So when we merge these two integrals or summing up these two integrals, we are getting triple integral over V curly F3 over curly Z dx dy dz is equal to the surface integral over S F3 dot product of n vector with k vector ds. And by symmetry, we can write the volume integral of curly F1 over curly X dx dy dz is equal to the surface integral of F1 dot product of n vector with I vector ds. And the volume integral of curly F2 over curly Y dx dy dz is equal to the surface integral of f2 dot product of n vector with j vector ds. Please mark this as 2, this as 3 and this as 4, and adding all these we get the volume integral of curly f1 over curly x plus curly f2 over curly y plus curly f3 over curly z dx dy dz is equal to the surface integral of f1 I vector plus f2 j vector plus f3 k vector and its dot product with n vector ds. This is further equal to the surface integral of, writing this as f vector dot product with n vector ds. Please mark this as 5. And now using the equation 1, we are going to use the equation 5 for the right hand side, that is equal to the surface integral of f vector dot product with n vector ds. So from 1 and 5 we get volume integral of divergence of f vector dv is equal to the surface integral of f vector its dot product with n vector ds. That is the result for the Gauss's divergence theorem. Alright, thank you.